Hello everyone, I'm Shipeng from Ant Group, and I'm currently the project leaders in FinBench Task Force. And I'm happy to announce that the financial benchmark is currently the LDBC official benchmark, which we just passed the vote for uh, the several days earlier, and it's now an official financial benchmark in LDBC. And here's my quick introduction to the LDBC FinBench. First, we are going to take a quick review to the financial benchmark. Okay. The motivation for us to design a new benchmark as financial benchmark is we find the SMB social network benchmark is designed based on the social network scenarios, and we think it's limited when applied to the financial industry. So the objective of FinBench is to design a high-quality benchmark for evaluating the performance of graph database systems in financial scenarios. It will include some scenarios in anti-fraud and the risk control based on the financial data pattern and the query patterns. Here is a list of the key features in the FinBench. From the perspective of data side, we have the power law distribution. We have the data age multiplicity, which means there are multiple ages from the same vertex, from the same source vertex to the destination vertex. And we have multiple hub vertices. And from the perspective of the transaction workload, which is for the ALTP scenario in FinBench, is a workload for ALTP scenario. In the transaction workload, we have some features, the read-write query, and we have some special graph patterns. We have the time window filtering, recursive path filtering, and truncation. I will explain them one by one. Okay, here is a brief of the initial version. In the initial version, we have all the key features in the last slide, which is also we proposed implemented. Yes. And for the workload, we have the transaction workload, including 12 complex read queries, 6 simple read queries, 19 write queries, and 3 read-write queries. For the data side, we have the data generator supporting to generate up to scale factor 10 data set. And for the implementation, we have 3 implementation on the systems, including 2 graph, GetSpace from CreateLink, and AutoGraph from Altipa. And in the initial version, it was designed and implemented with 9 vendors in the task force, and we have around 6 developers to develop the benchmark suite. Okay, let's go to the data design first. Here is the data schema for the FinBench. We have 5 vertex type here and 9 age type here. You can see the the data schema is mainly about some financial entities and the financial activities. The dashed arrow here means the single ages from source to desk. For example, between one person vertex and the another account vertex, there will be only one age from the person to the account. And for these arrows means the ages is there will be multiple ages from the source to the vertex. For example, the transfer age from one from one account vertex to another account vertex, there will be multiple transfer agents from the source to the dest. And here is the data distribution of the transfer agents, which is the main the data agents in the data set. And the distribution is defined as the power law distribution. And in the schema, it's also the asymmetric directed graph. And we just do some simple profiling based on the data generated by the generator. And you can see we have the average degree of around five to six. It's an average degree, and for the average multiplicity, there will be it's around 1.6. Okay. Here's we are going to look at the transaction workload. The transaction workload is the scenario is about the financial activities among the vertices. And for the queries, we have 12 complex read queries. The complex read queries match exact patterns, including the cycles and the trees, starting from one or two vertices. And we have 6 simple reads discovering the neighborhood of some nodes. And we have the 19 write queries, including inserts, updates, and deletes. Here the deletes are cascade deletion. And we have 3 read-write query, which is a key feature in the transaction workload. In another word, it's a kind of transaction wrapped complex reads. Here's some example patterns. I just list some complex queries from the transaction world here, and you can see we have some cycle matching, some tree and chains. Okay. This slide is talking about the time window filtering. In the ages in the data schema, most of the ages have a property of the time step. And the fact in the financial scenario is the queries only look back in a limited time window. For example, here is the complex query 1 in the transaction workload. The target here is to find, starting from the giving accounts, and find all the blocked medium within the 3 hops from the neighborhood. And since the queries only look back in the limited time window, so when we traversing the graph, we will do the filtering, like filter the age between start time and end time in the traversal. Here is about the recursive path filtering. Recursive path filtering is a key feature when we find some trees and paths in the graphs. Sometimes we need to find some transfer trees from one given node. For example, when a loan is applied and the fund and the money will transfer from the loan and to the next account, and one by one to the following stream. And assuming we have a trace from A to B to X, so the timestamp order of this trace will increase in the trace, and the amount order of the ages in the trace will decrease. Here I'm going to talk about the redirect query. Redirect query, as I just talk about it, the redirect query is the transaction wrapped complex reads. It's in the scenarios. It's about the read control strategies. Uh, for example, here we start from the age where when the transfer happens from the source to the desk, uh, we won't write the age directly to the storage. We will perform it in a transaction. Firstly, we to well match the pattern if the strategy here, which is a complex query, we will match if there is a cycle formed with a new edge insert to the graph. And if the transfer cycle is formed, we think this edge is have some problems. So we just about the red transaction and to mark all the related accounts as blocked. And if not, we didn't match the transfer cycle, we didn't match the transfer cycle, the transaction will committed and the transfer age will actually write to the storage. And here is about the truncation. Truncation is a strategy we use to control the computation complexities when we traversing on the graph, especially when we traversing on the hypervertex. Uh, the thing is, we just like to truncate less important edges to avoid the complexity explosion when traversing the graph. And truncating is actually a sampling. To make the sampling deterministic, we defined two variable, the truncation limit and the truncation order. Truncation limit and the truncation order is defined to ensure the consistency of the result. For example, when we traversing from the source to the desk, we will keep only the top 100 edges in the order of the time step properties in the descending order. Okay, here we come to the section of the benchmark suite. In the initial version, we have the data generator is able to generate the data from the 001 scale factor and scale factor 10. And all the data set that we generated has published at the Google Drive, and the data set is generated using the CSV serializer. And in the future, we are going to improve the data generator to support larger scales. And for the benchmark driver, we inherited the implementation from the SMB interactive driver, and it also has three mode of operations. It can generate the data validation data set, and the second main function is to validate the implementation with the data set validation data set generated. And the next is to execute a benchmarking to the SUT, to the system under test. And in the initial version, we have three implementation on two graph and Galaxy Space and Algebra graph. And the implementation of two graph and the Galaxy Space are in Cypher. The implementation of algebra graph there is a precisely designed language by the algebra team. It's UQL, and all the systems in the all the systems have passed the cross validation, and the two graph and Gatsbase have the benchmark results in the reports. You can refer to the report and the packages in the link here. And here is the roadmap of the financial benchmark. The initial version is just the beginning of the financial benchmark, where the key feature here is to include all the proposed features in FinBench proposal. And in the initial version, we will have the benchmark suite developed to make the FinBench runnable and auditable. And in the following versions, we are going to support the large data scale, and we will optimize the parameter creation stage to choose the query parameters better. And we are going to do some profilings about the query mix pattern and redesign these features in the benchmark driver. And in the future, we are going to design a new workload, the analytic workload, which is more complex than the transaction workload. And in this initial version, I would like to thank all the task force members. We have 9 task force members here, and we have 6 developers here to support the development of financial benchmark. I would like to thanks to their contributions. And here I list some links about the financial benchmark resources, including the specification, the benchmark suite, and the audit packages and the data set. Yes, okay, that's all. Thank you. Is there any questions?
Thank you. That's great work and much appreciated, and hopefully it will be adopted widely very soon. Let's see if there are any questions in the audience. There is one from Ben.
In the next version, what scale factors are you looking to go up to?
The question is, what scale factors are you looking to go up to in the next version?
In the next version, we are going to improve the generation process of the financial data, and in the near future, we are going to support the up to scale factor 300, and we are go to the larger scale when we design the analytic workload.
How many gigabytes is that? Like, is that 300 gigabytes?
Yes, so it's the same definition of scale factor, 300 gigabytes of CSVs. I saw a hand, Minchi, maybe?
What's the factor scale?
So what is the current scale factor that you support?
The current scale factor we support here is we run the cross validation on the scale factor 1, and we run benchmarking on scale factor 10.
Okay. Yeah, go on. Yes.
Yeah, so this is Christopher from Leipzig University. So I'm doing research in temporal graph analytics, and I'm really glad to see that this data set, your schema, has timestamps everywhere in the code schema. So now I'm interested in your Google link. So where can I find it when I don't have your slides now? Because I looked at the website of LDBC and it's not available. So where we can download the data.
I'm sorry, you find what? What
you posted, you showed us a Google link drive, a quite long one. So is that anywhere available to click on it from outside? So you have to send us the slides and then
we will upload them.
Oh, you will upload them. Oh,
yeah,
perfect. Yeah. Yeah, really interesting. Thank you.
Yeah.
Okay, thank you.
The software will be open source. I mean, it should.
It is already open source. And we are also collaborating to make the data sets available with no egress costs and very seamless way to download.
Can I ask?
Yes, go on.
Shipeng, thanks for this for leading the work on the financial benchmark. A question for me also on the data generation.
Okay.
So if you want to scale this, I think 300 gigabytes is still not very large actually for CSV. Yeah, the SMB goes up to, I don't know what, 10,000, 30,000 now. And for that, okay, it uses Spark, I think, because yeah, you would need a distributed system to generate data in parallel. Do you have like, I mean, if you say that you will fix this, but your target is only 300, I mean, are you going to make a parallel and distributed data generator for this?
Yes. In the initial version, we will not implement the data generation upfront. There are some problems in the data performance, and it's mainly because the data schema compared with SMB, we have less we have less less properties which can inflate the data, and in order to generate larger scale of the data, so we needed to implement the performance, and yes, I actually considering to generate it in parallel. Yes.
Yeah, I think it must be parallel nowadays. Otherwise, it's will not be very usable. Success.
Yes, it's currently I just implemented it in the Spark, and I think it's good to extend it to improve the performance. Yes.
Okay, excellent. Final question on the FinBench, anyone? Okay, seeing no questions, thanks Shipeng for the talk and the great work too.
Okay, thank you, Gabriel. Thank you all.